Okay, so um, every once in a while in class I'll make a video. Pretty soon I'm going to start recording the lectures so that they're available to everybody in class. Before I actually get a webcam, though, I'm going to make a few videos on Doceri Desktop. So, first section for this quarter in the textbook is 4.1, talking about what angles are and how to measure angles, either in radians or degrees. So first, let's actually take a look at what angles are, how to form them, and some terminology that involves angles. Okay, so here I am in the textbook here. This is just, the beginning of chapter 4, unit circle trigonometry, and in this section we're going to talk about angles and their measure. And to get a good sense of the definitions of what angles are, there's a really nice interactive figure. Now, if you want to construct what we call positive angles, you start with a vertex. In this case, I've just chosen the vertex of the angle to be the origin in the xy plane, so that's this dot down here. Okay. And every angle has what's called an initial side that you use to form the angle by rotating that initial side. Now, most of the time, the initial side of the angle is located on the positive x-axis. Now, I can start out by having a no angle at all, so the initial side and the terminal side would be the same, and then what I can do is I can start rotating that initial side counterclockwise. That'll correspond to a positive angle. Okay, so every angle has a vertex, initial side. The initial side gets rotated, keeping the vertex fixed. Wherever you stop, that's what you would call the terminal side of the angle. We can also switch and take a look at negative angles. So again, if you start at your initial side and you start rotating clockwise, you would be forming negative angles. Okay, and again, so you take your initial side, you rotate it clockwise, and then once you finish rotating, the initial side becomes the terminal side. This next interactive figure just describes a few different types of angles. So first of all, again, you just have this, so here on the right side, you just have an angle that's been formed. It has its vertex, it has its initial side in standard position, horizontally on the x-axis, and then it's been rotated counterclockwise, so this would be a positive angle. And again, you can come in here and you can mess around. You can move the angle all the way around if you want. Okay, so here we're just looking at positive angles, so I can form any angle. An acute angle is one that results from a rotation that is less than 1/4 of a complete counterclockwise rotation. Okay, and we're going to see later that this is an angle that is anything less than 90 degrees or pi over 2. You could have a right angle, and that's one that results in a 1/4 of a complete counterclockwise rotation, and we'll see later that right angles are ones formed by rotating by 90 degrees or pi over 4. An obtuse angle is one where you've rotated more than a quarter way around. You've made more than a quarter and less than a half of a complete counterclockwise rotation. You have what's called a straight angle. That's if you rotate half the way around. A reflex angle is one that's been rotated more than a half but less than a full rotation. And then a full angle is just rotating all the way around and landing back on your initial side. So we'll see in a moment that this is an angle. A full angle in terms of degrees is 360 degrees, and in terms of radians, a full angle is an angle of 2 pi. Now, before defining, before defining what the radian measure of an angle is, I think this figure is really nice in the textbook because it really illustrates that the radian measure of an angle is really just the ratio of the arc length over the radius itself. So here, notice you've got an angle that's formed that's pi over 4. If you look at the picture on the bottom right, if you trace out that, if you start at the initial side and you rotate by pi over 4 radians, okay, that traces out an arc length of pi over 2, so that would be the distance traveled on the edge of the circle, and the radius here would be positive 2. And you could notice if you take the arc length divided by the radius, so pi over 2 divided by 2, you will get the angle measured pi over 4. Now, what's interesting is you can, if I halved the radius, so say I go back to a radius of positive 1, you'll notice that the arc length has also been halved. Okay, so the angle stayed fixed, and if you increase the radius, the arc length has to also increase. Okay, so the distance around the circle increases as well. Okay, and when you look at the formula for the definition of what a radian is, it's the radian measure of an angle is the sine length s of the circular arc associated with theta, and then you divide by the radius of the circle. The circular arc length s is going to be positive when you have positive angles when you've rotated counterclockwise, and negative when you've rotated clockwise. So, coming back to the picture up here, you can see it a little better. Right, in this case, we have a counterclockwise rotation, so it's a positive angle theta. So you can see that the arc length s also has to be positive. If you were to consider a negative angle, let's see if I can get negative. Okay, well, either way it doesn't really matter, but now you can see that the angle here has to be negative if you look in the box for the angle theta. And to compensate, if you look at your formula s over r, the radius is always going to be positive. For the angle to be negative, the arc length would also have to be negative. Okay, so let's actually just do a couple examples of this. So given any two of these three quantities, the angle itself, the radius, or the arc length, you should be able to recover the third. Okay, so again, let's just summarize before we do an example. So the radian measure of an angle is always equal to the signed arc length s divided by the radius of the circle that you're on. Okay, now for example here, if I just want to do a few examples of finding an angle. Okay, so again, we know that theta is the signed arc length divided by the radius. So for example, if we want to find the radian measure of an angle theta corresponding to an arc length of 3 pi over 4 on a unit circle and a radius of 2. Now since the signed arc length here is positive, it's 3 pi over 4, that means that our angle as well is going to correspond to a positive angle. Now if I want to find the radian measure of the corresponding angle, it's going to be the signed arc length 3 pi over 4 divided by 2. Dividing by 2 is the same as multiplying by the reciprocal 1/2, and we end up getting 3 pi over 8. Okay. So on the circle of radius 2, if you've rotated by an angle and end up with an arc length of 3 pi over 4, then the angle in radians has to be 3 pi over 8. So another thing that you might be asked is, instead of being given the arc length and the radius and being asked to find the angle theta, you might be able to ask to find the arc length associated with a particular angle on a circle of a particular radius. So for example, we could find the length of the circular arc corresponding to an angle of minus pi over 4 radians on a circle of radius 4. Now, what you're going to do first, and this is with any math problem, you're going to write down any relevant equations, formulas, any information that involves the variables or the quantities mentioned in the problem. So since I'm trying to find the length of a circular arc, I've been giving an angle of minus pi over 4 in a radius. We should know right away the pertinent formula to use or work with is the formula for the radian measure of an angle theta, which is the arc length over the radius r. Now, since we're trying to find the arc length, if you solve this formula for the arc length s, you just multiply both sides by r, and the arc length always just ends up being the radius times the angle itself. So for us here, the arc length is going to be the radius of 4 times the radian measure of the angle minus pi over 4, and you end up getting minus pi since the 4's will cancel each other off. Okay, so we have rotated pi units in the clockwise direction. If we've traced out we have traced out an arc length of pi units in the clockwise direction if we've rotated by an angle of minus pi over 4 on a circle of radius 4. Okay, so anytime you're given two of these quantities and you're trying to find the third, it comes down to using your formula for the radian measure in terms of arc length and the radius. Okay, so now what we're going to do is talk about the radian measure of a rotation. We'll also do this for degree measures of rotations in just a moment. But the radian measure of an angle generated by one complete counterclockwise rotation is 2 pi. Okay, so if I start at my initial side of the angle and I make one full complete counterclockwise rotation, you will get all the way around and land back on your initial side again with your terminal side. The radian measure of an angle generated by a fraction of a complete rotation is just the fraction of the rotation times 2 pi. If the rotation's counterclockwise, you're going to take the fraction to be positive, and if the rotation is clockwise, you're going to take the fraction of rotation to be negative. So let's do a couple examples of this. Okay, so for example, if I want to find the radian measure of an angle generated by a 3/4 clockwise rotation, if you look back just a minute ago when we looked at the formula for the radian measure given by a fraction of a rotation, if we're going to be rotating clockwise, we're going to want to take the fraction of the rotation to be negative. Okay, so recall here, the formula for the radian measure of an angle is taking p, that fraction of a rotation, times a full rotation, 2 pi. And for us here, since the rotation is clockwise and we're going 3/4 of the way around, our fraction of the rotation is going to be minus 3/4. So our angle theta here in radians is going to be the minus 3/4 times 2 pi. And then multiplying -3 by 2 pi is going to give you a -6 pi in the numerator divided by 4, which simplifies to minus 3 pi over 2. Okay, so if you go 3/4 of the way around in the clockwise direction, that corresponds to an angle of radian measure minus 3 pi over 2. Okay, so definition in the textbook, in the section corresponding to degree measure, an angle of measure 1 degree corresponds to a counterclockwise rotation of 1/360th of a complete rotation. And the reason for this is because to go all the way around, you would want to rotate by 360 degrees. So going 1/360th of the way around is going to be, that's going to correspond to an angle measure of 1 degree. Now, if the formula is the same for a fraction of a complete rotation, the angle measure in degrees is going to be your fraction of the complete rotation. With the same convention as before, it's positive if you rotate counterclockwise, p is negative if you rotate clockwise, and then you multiply that fraction of the complete rotation by the 360 degrees. Okay, so for example, let's find the degree measure of an angle formed by a 3/2 counterclockwise rotation. So this means that you are rotating 1.5 times, so 1.5 times the complete rotation, and we're going in the counterclockwise direction. Now again, remember theta in degrees. is the fraction of the rotation p times 360 degrees itself. Now for this problem, since we're rotating counterclockwise and we're doing a 3/2 rotation, our p is going to remain positive 3/2. So theta in degrees is going to equal 3/2 times 360 degrees. Little arithmetic here. 3 times 360, I believe, is 1080 divided by 2 degrees. And this will equal 540 degrees. So going 3/2, making a 3/2 counterclockwise rotation corresponds to rotating by an angle of 540 degrees. Okay, so what if this time instead of giving you the fraction of the rotation and I want to find the degree measure, this time I give you the degree measure of 160 and I want to know what fraction of a complete rotation that is. So again, you want to look at your formula. Theta in degrees is the fraction of the rotation times the full rotation of 360 degrees. You can solve for p by dividing both sides by 360 degrees. Okay, and since our theta in degrees is 160, we will divide that by the full rotation 360 degrees, and this ends up just being 4/9. So a 160 degree angle is the same as making a 4/9 counterclockwise rotation. So the the next topic that I'll discuss is this idea of coterminal angles. And what coterminal angles are they're angles with possibly different radian measure that have the same terminal side. So for instance, the interactive figure in this section, if I start with an angle theta equals pi over 4, we're on the unit circle. That's a circle that has radius 1. Okay. If I start with the angle pi over 4, what you'll notice is if I want another angle with the same terminal side, I just need to take my original angle and then just start either adding or subtracting complete rotations. So if I want to start with the angle pi over 4, I can start with that angle and add a complete rotation to it, which is the same as adding 2 pi. And then that'll give me the angle 9 pi over 4. I could do the same thing again to obtain another coterminal angle. I could take 9 pi over 4 and I could add 2 pi again, and now I've started with my angle pi over 4 and I have now rotated from that angle 2 times. I've made 2 complete rotations. Okay. Another thing you can do is now I can start subtracting 2 pi's. I can take one of those complete counterclockwise rotations away to get back to 9 pi over 4. We can subtract another 2 pi from 9 pi over 4 to get back to our original angle pi over 4. And I can keep subtracting 2 pi's. So here I've got a minus 7 pi over 4, a minus 15 pi over 4, a minus 23 pi over 4. If you just notice, you're just either adding or subtracting 8 pi from the numerator each time, since 2 pi is the same as 8 pi over 4. And you can keep doing this forever. There's actually infinitely many coterminal angles for a given angle. So let's do an example here. So if I want to find an angle, say in the interval from 0 to 2 pi, coterminal with the angle negative pi over 3 radians, that corresponds to a clockwise rotation, you will notice that in the interval 0 to 2 pi, that would consist of only positive angles between either no rotation or a full rotation. So what you're going to do is, to find a coterminal angle theta, you can just take your minus pi over 3 and add a full rotation 2 pi. That's the same as minus pi over 3 plus, if you get a common denominator, 6 pi over 3, which is going to leave you with an angle of 5 pi over 3. Okay, or another way you could write this is you could write this as 5/3 times pi. Okay, so that would be an angle coterminal with negative pi over 3, and notice that 5 pi over 5/3 pi sorry, that's coterminal with minus pi over 3, but the 5/3 pi is going to be less than 2 pi because 5/3 is less than 2. Okay, so that is in the given interval that we are looking for. So I'm going to, well, actually, one more comment. If I go back to the textbook and I come down here, in general, so what I did in that previous example is we took our given angle and I added one complete rotation to get a coterminal angle in the given interval. But really, for any integer k, a given angle theta is going to be coterminal with that given angle theta plus any multiple of 2 pi. So the integer k is just telling you how many times you're rotating and in what direction, right? So if k is equal to 2, that just means that we're taking our angle theta and adding 2 complete rotations to it. If k was equal to negative 3, I would take my angle theta and I would be subtracting 3 full rotations. So in general, I can add or subtract any number of full rotations to an angle to get a coterminal angle. Now, I'm going to stop the video there for now. There's a couple more things I need to wrap up in section 4.1. We need to talk about how to convert angles from radians to degrees and vice versa. And then I just want to do maybe an application problem or two, and that'll wrap up section 4.1. So I'll either get a video posted here in the next day or two, but thank you for watching and tuning in, everyone.